we're going to continue looking at section 1.4. This is day 2 for Calc Honors. So let's go ahead and keep looking at some information. Yesterday we looked at continuity. Today, more specifically, we are going to look at discontinuities. Okay. There's two types of discontinuities. There is removable and there is non-removable. When you're thinking about removable, the limit still exists. Where non-removable, the limit does not exist. Okay, so an example of removable could have a hole in the graph. An example of non-removable, you could have an asymptote. You could have a jump or oscillating behavior. Okay. So let's look at a couple of examples of removable and non-removable discontinuity. So let's say that I ask you to look at the graph and also find the limit as x approaches 3 of x squared minus 5x plus 6 all over x minus 3. All right, so if we're finding the limit, the first thing you do is if you plug in 0, you notice that you're going to get, if you plug in 3, excuse me, you're going to get 0 over 0, which is indeterminate. Okay, so we need to use one of our 4 strategies, so we're going to factor and cancel. Top factor is to x minus 3, x minus 2. Therefore, we can see that we can cross off the x minus 3's. So our limit is going to equal 1. Okay. In this point here, we had a removable discontinuity. And the reason being is that the limit still existed. Okay, if you're thinking about this graph, it's actually just a linear equation, x minus 2. But there's going to be a hole in our graph at x equals 3. Okay, so if you were graphing it, you'd start here at negative 2, go up 1 over 1, up 1 over 1, and then at 3, 1, there's going to be a hole in my graph, 1 over 1, and so forth. Okay, so you can see that this graph has a removable discontinuity, and we could say that it is continuous on the interval using interval notation negative infinity to 3 in union with, or and, 3 to infinity. At 3 we have a hole, so our graph is not continuous. All right, look at another example. Let's do a piecewise function. All right, so first let's look at the function just itself. So if f of x equals, and there's going to be 3 pieces to this one, 2x minus 1 if x is less than 2, 4 for x equals 2, and then 1 half x plus 2 when x is greater than 2, and I'm going to ask you to find the limit as x approaches 2 of f of x. So let's actually first draw a picture of this graph. Go from y-axis -1, 4, and on the x-axis like 0 to 5. Okay, I'll use different colors to represent our graph. All right, so this first one, when x is less than 2, 2x minus 1. So I'm going to start here at -1, go up 2 over 1, up 2 over 1. I'll have an open circle at that this spot. Okay, let's see, when x equals 2, it's going to be the ordered pair 2, 4. And then this last one, 1/2 x plus 2. So if I plug in 2, let's see, I am going to get 3, so it's still an open circle at this spot. If I plug in 3, actually let's plug in a value, it's a little bit easier. If I plug in 4, just plugging in 4 this equation, so 4 over 2 plus 2, I am going to get a 4 as well, because I get 2 plus 2. So the ordered pair 4, 4. See, my slope is up 1 over 2. Okay, so here is the next section of my graph. Alright, so let's think about what the limit would be as x approaches 2. Let's look at the right hand and left hand side limits just to kind of talk about this a little bit. So the limit as x approaches 2 from the right hand side of f of x, so I'll be using the green function, the 1/2 x plus 2, that would equal 3. The limit as x approaches 2 from the left hand side of f of x, so that'd be the 2x minus 1, that also equals 3. Therefore, the limit as x approaches 2 of f of x, we have the same value from the left and right, would also equal 3. Okay. In this case here, we have a removable discontinuity, x equals 2. And the reason being is that we have a hole. We could say that this function is continuous on the interval from -infinity to 2 in union with 2 to infinity. Okay. All right, so let's look at some examples maybe where we have non-removable discontinuity. So let's say we had the limit as x approaches 2 of 1 over x minus 2. So if you think about this graph, we know we have a vertical asymptote at 2 here. Oops. Okay, so and we know this graph looks something like so. Okay, so therefore we can see that as we come from the left and right hand sides, different values, positive and negative infinity, so the limit is not going to exist. So right away we know that we have a non-removable discontinuity. And our function, we could say, is continuous on the interval from -infinity to 2, union with 2 to infinity. Okay. All right, last example. If I ask you to find the limit as x approaches 3 from the right-hand side, I think you have something like this in your practice problems, so I just wanted to look at with you the absolute value of x minus 3 all over x minus 3. So if you think about this graph, okay, we can see that if we plug in 3, we're going to get 0 over 0, so it's indeterminate. If I plug in 4 to my function, I'm going to get 1 over 1. If I plug in like 3.5, I get 1 over 1. So basically what's happening is it's a horizontal line, y equals 1 from the right-hand side. If I plug in, let's say 2, I'm going to get 1 over -1, so it's going to be here at -1. So I have a horizontal line as I come from the left-hand side at y equals -1. Okay, so if we're looking as x approaches 3 from the right-hand side, this would just equal 1. However, this is a non-removable discontinuity, and our function would be discontinuous at x equals 3. All right, if you have any questions, please let me know.